panel talk of the morning session, which is Birgit Stiller here from MPL.
And also thanks for giving me the opportunity to talk here at home, let's say, at the Institute. So I'm going to talk about reconfigurable optical neural networks, and our group is working on acoustic waves for different applications, and one of them is towards optical computing. I want to highlight already all the people that are in several aspects of the work involved. And the first five up there, they are also at the conference, so please talk to them at the posters and in the breaks. Okay, so we are using acoustic waves, but in combination with optical waves. And so usually when you have guided waves, you can have them in optical fibers or in waveguides on a chip. So you see here different types of optical fibers and the optical modes. But you can also have guided acoustic waves. So these can be of different types. For instance, longitudinal waves, which are these pressure waves, they just propagate along the waveguides. Or you have shear waves, which is like breathing modes of the fibers or the on chip. They are a bit similar to optomechanical resonators. So they are resonators in a resonant box like an instrument. And you can also have flexural waves, which are kind of hybrid between them. And there's an interaction possible of both of them, even if the physics is quite different. So acoustic waves and light waves have different velocities, usually are treated in different frequency regimes, but the wavelength is in the same order of magnitude, that's micrometers. And that is where also you can enhance and also inhibit this interaction, for instance, through microstructures. They are also sensitive to different parameters, and that's quite interesting also for computing, because, for instance, acoustic waves are quite sensitive to pressure, to strain, to temperature. So you could use them at the same time as an input and already do processing while you are actually sensing. They have also different guidance mechanisms, but this doesn't concern us today, I would say. The effect that we are using is actually a detrimental effect for telecommunications. So usually this limits the throughput in optical fibers, but we are using it advantageously. Because what happens usually is if you send light into an optical fibers and this gets very strong light, you will have everything back reflected. So that limits your systems usually. It's a third order nonlinearity and it involves two optical waves and one acoustic wave. So when you shine light into a waveguide or an optical fiber, you get back reflection from vibrations at room temperature, and you have back reflected light that is downshifted in frequency or upshifted. This is, you can imagine it like the Doppler effect. Basically, the acoustic wave is moving. What is important is that you can also excite these acoustic waves at very high frequencies, as gigahertz, with counter-propagating light waves. By obeying energy and momentum. And what is important to take away at the beginning of the talk is that we are not using resonators, so we are not bound to several resonances in the system. We can talk to a continuum of acoustic waves and can sweep the wavelengths over the whole transparency window of the waveguide. And we also don't use transducers yet. So everything that is there is just an optical structure. There are no transducers inducing acoustic waves. There has been a lot of research in this field, starting actually to become very lively with Brion scattering in photonic crystal fibers here actually at the Institute, in nanotapers, in fibers that are filled with gases or with liquids. And then it became also, it was also exploited on a chip, starting with soft glasses and other materials, silicon nitride, silicon, and very interestingly also on thin film lithium niobate. That's interesting because you can also couple them to the electronic domain. And it was also explored in combination with superconducting qubits or also acoustic metamaterials, where one can talk not only to gigahertz acoustic wave, but even to terahertz acoustic waves. Okay, so in my lab, we use optoacoustics for different applications, and I will focus today on the computing part. And we also work on quantum information processing. I will highlight one project here. We are using liquid core fibers for thermodynamic sensing. And we have also a project on magnons and on-chip devices, and on non-Hermitian physics. And I will also mention a bit of these because they have some bridges to the computing direction in our group. Okay, I wanted to highlight some alternative computing approaches because I didn't know how many approaches will be actually covered in this conference. I'm often attending the photonics conference, so I see the photonics approaches, but there are also people doing computation with mushrooms, for instance. And before thinking that is crazy, you could also think what actually happens if there's no electricity anymore. So for some let's say outage, I don't know, for some catastrophic events, it might be actually interesting to have concepts where you don't need our infrastructure. You can also do storage in DNA. One can also use organoid intelligence, so cell cultures that compute inputs, like on a tiny Petri dish. So that's very interesting, and I was also interested in, I saw in some talks there will be also non-photonic approaches, so that's cool. Okay. I don't have to motivate us, that's the motivation of the conference. But why photonics? And that's very similar to motivation also for telecommunication. It's the bandwidth, you can do parallel computing, you have some computation for free. And if you want to have a broad overview, I would recommend this roadmap, and there are still people missing, but this gives you already an idea. And so we were asking ourselves, can acoustics add some features or also replace functionalities in this realm? And just to say what the vision is, we want to develop a new hardware. It's less using machine learning, which would also be interesting, but we really want to work on a new hardware that is doing computation. And so why photonics, why acoustics? I have some reasons for that. So first of all, it's reconfigurable, so the acoustic waves can be excited, and they also disappear. So if you think about some acoustic structure that is there, it will just disappear if you don't do anything. You don't need any fabrication with it. It works in optical fibers or in waveguides. You have different time scales. So if your light is very fast, your sound is quite slow. So if you want to have some recurrency, that's very interesting. It's all optically controlled. So all the pulses are externally generated and sent into the device. It's coherent in phase and amplitude. You can do frequency selective computing because the interaction is very narrow line width, so you have only 20 megahertz of a line width, so you can address frequency channels. It's integrable, scalable, and you have the sensory input from the acoustic waves directly. So I'm going to talk about these topics today. First of all, I will mention the photonic activation function that we were working on optical memory, using the optical memory for recurrent neural networks and in situ training, and at the end, on extreme learning machines and time-delayed reservoir computing, which are quite new topics to us. So we were thinking, and I was actually inspired by a talk at Photonics West by Logan Wright more than a year ago, where he was preaching we need to upscale in the photonics community because otherwise we are not going to prove that we are actually energy efficient. And so there are different approaches to upscale, I guess, and one thing we were thinking about in the fiber approach is that we go to many layers. But if we go to many layers and our activation function is in an OEO, like Dimitri told us today, we are going back to the electronic domain. So for us, it made sense to think about an all-optical idea of a nonlinear activation function. And acoustic waves can provide these. Such a double-stage setup that you see here. And we have different knobs, for instance, the power of the amplifier, the length of our fibers, and others, where we can actually go to different types of activation functions which correspond to some that you know, like a sigmoid or others. And this means that you have a quite high nonlinearity between the input and the output of this scheme. Interestingly, it can also work for different frequency channels because I mentioned this narrow line width. So we show this for 2 frequency channels, but this can actually go also for a frequency comp. So we imagine this a bit like you have a certain optical neural network structures and you could impose it on top and even have an activation function for each frequency channel if you wish for some tasks. Okay. Now I was talking about the different velocities in optics and acoustics, and so it's not far away to think about memory. And there has been quite some approaches to this for optical memory, for instance, non-volatile, like based on phase change materials, nanocavities, or I would recommend this review where they talk about all different approaches of doing non-volatile and volatile memory. Our approach is volatile because, as I said, the acoustic waves disappear after a while. And how does it work? So you would have your information in the optical domain going into your optical fiber, and you have counterpropagative pulses that would transfer this information to the acoustic domain. There it's propagating much slower. And then in a second step, so 5 orders of magnitude actually, in a second step you would read these pulses in the acoustic domain and get the information back. It also means that these acoustic waves stay much longer in the material than the light would do. Features are, for instance, it is coherent, so you can store phase and amplitude. It is variable in memory time because it depends on your external pulses. It's all optically controlled. I mentioned you can use it at different frequency channels. It's quite, you can get actually quite close, like 100 megahertz. It is non-reciprocal because the acoustic wave has a direction. So it means that you will process the light in one direction, but if you do the same in the other direction, if you have information in the other direction, it doesn't work. So that's also interesting for some approaches. You have quick access and it's non-degrading. You can do it all and over again in your fiber. Challenges are, for instance, to extend the storage time because the storage time depends on the dissipation of the acoustic wave and the capacity, so how much information you actually can put into your acoustic wave. So we've been working on the extension of the storage time, and there are different options. For instance, we were working on one where the information is in the acoustic wave, and then we enhance the acoustic wave optically from the outside. So it's like refreshing the information, and that works. We were also working on a passive approach where we cool down the optical fiber, and we see that instead of having 10 nanoseconds like at room temperature, one gets to almost 150 nanoseconds. So that's also something that's interesting in the quantum domain suddenly. In terms of capacity, one can think about the phase space. So thinking about different phase states, like a QPSK signal, and you would retrieve, for instance, after 6 nanoseconds or after 70 nanoseconds at cryogenic temperatures, the different phase states and the differential phase between them stays the same. But not only this, you can do actually more. If you are in resonance at your Brion frequency shift, you would read out the same phase that you have stored, that it was in your original pulse. However, if you detune from this resonance, you will be able to actually read out a different phase. So that's why you have these spirals here. So what does it mean? It means that you have a memory, your information is in there, and you can control from the outside which phase you are actually extracting. So it's like processing your information inside the acoustic memory. And we use this for training. I will mention this later. Another idea of extending the capacity is, for instance, to go to higher order optical modes. And we started with polarization modes, and was the easiest for now. You have, for instance, 2 data pulses which are encoded in 2 different polarizations. And depending on your control pulses that are counterpropagating, you can either address one or the other, or even both of them. So for instance, you have here these 2 polarization channels, and with one, for instance, right circular polarized control, you would address the one, for the other one, the other channel. And if you use linear polarized light, you can actually address both of them. So you see there's something happening to both pulses, and you have a readout. Now, if you have a memory, this might make you think about recurrent neural networks, which can actually process also the context of the information, not only the information itself. And in optics, that's very often implemented as cavities, as delay systems, or as, or for instance, microring resonators, so as structures. And these structures are basically there, and also if you might not need them, they are still there. And so we were thinking, can we do this in a volatile manner, so we could induce a recurrency, and if you don't need it, then it's gone, so to say. And we can do that with acoustic waves. And the concept looks the following. So we would have information going into a fiber and passing through, but this is less than in the beginning. It would couple via control pass to an acoustic wave. In a second computational step, you would have a second acoustic wave. Both acoustic waves interfere with each other, and so on and so on. And it means that every computational step has a link to the previous one. And that works as long as your acoustic wave is alive. So let me give you more of the technical setup of that. So if you have, for instance, a highly nonlinear fiber, you would send in a data sequence from one side and your control sequence from the other side. And at the same position, you would always have like two of them meeting. And so the acoustic waves are there vibrating and interfering with each other. You can also do this at different positions. That's sometimes advantageously, sometimes not. But you can prevent it if you have a shorter fiber, for instance. Okay, and as a first proof of principle, we implemented an easy task. So we would have different amplitudes on two optical pulses. And with the third one, we want to classify and want to know what the amplitudes were before. And that works surprisingly well. If you have your acoustic waves off, you're basically guessing. And when you switch them on, it gets to almost 100%. So that works nicely, but it was only a very simple task. One can go to a longer pulse range, for instance, 3 pulses, and there you also see a good increase in accuracy. If you go to cryogenic temperatures, even better. But we were still not so happy about 67%, I have to say, so we were thinking, can we do something about this? And I remind you back to our phase readout, and we thought we could actually train this. And Jesus will have a talk tomorrow about it, so he will give many more details about this. As you see here, the amplitude is changing, but obviously we can also normalize this, so we care only about the phase, and you can actually read out the complete phase space. What does it mean for the setup? Instead of having a resonant operation where you would be at the peak of your Brownian frequency or spectrum, you would actually go away from it. And then you can actually read out a different phase. And there they got to amazing more than 90%, and have also in the overlap of these signals that you want to distinguish, you would also have a nicer distinction. Another feature that we were testing in for the recurrent optoacoustic operator is how much can we actually connect optical pulses? Because at room temperature, let's say if the acoustic lifetime is 10 nanoseconds, you get 3, 4, maybe 5 pulses. But if you get to cryogenic temperatures, you can have more. And so what you see here at 20 nanoseconds, it's almost flat, so you don't have any interaction. But if you go to cryogenics, then you still see something at 100 nanoseconds, and only there it's almost flat. And so what they also recently achieved to see in the lab is a connectivity of 20, so having the first pulse still have an influence on the 20th pulse. And that's pretty cool because you can then also process a lot of information. But I recommend the talk tomorrow. Okay, so now we have an activation function, we have a memory, we look at recurrency. Now we were also interested on this very narrow line width and what can we do for multiple frequencies with it. So how would one build an optical neural network? And at the last version of the workshop, I remember Daniel Brunner explaining top-down, bottom-up, and everything. And so one can have different options to do that, obviously. So either to think about what are the transformations that you want to have and then code it, or you take a physical system and use it and then choose what you actually want as a transformation. And so we were also working in towards this direction because we found this very interesting. And so what you see here is like a typical reservoir for computing where you have different connectivities and fixed weights, and you would train the readout layer. But one can also have a time-delayed reservoir computer, where in this case you have like a string of neurons and they run in a cavity. And you would still have the same type of training, but you can apply a mask on top of it to encode your weights. There will be a poster today by Diana, so have a look later today. So how is this? So in this case, OEO is not optoelectronic conversion. It's an optoelectronic oscillator, so it's, sorry, the same abbreviation. So what is it? It's a cavity which is half optical and half electronic. And since it's a cavity, it's still resonating. So you have cavity modes which you can detect at your output, either electrical or also optical. And there are two modes of operations. One is you use it in a low gain operation where you will be able to have a very nice microwave source. And this broad spectrum is a bit misleading. It's actually millihertz, the line width. So you can build it actually also in a very small footprint, so that's very interesting. But if you go to high gain, it becomes chaotic. So you have a lot of nonlinear dynamics. And actually in this paper, Laurent Larcher, they actually showed that it's possible to use this for computing. And we found this very interesting because there was a work on optoelectronic oscillators where one can use Brion scattering to tune the frequency of this very nice microwave source. So why is this beneficial? Because usually you would use an electronic filter here, which is fixed in bandwidth and has quite some losses, and you cannot tune it very easily, or not at all even sometimes. So if you use as a filter Brion scattering, because it's so nicely narrow line width, you can actually tune it all over the band, the telecom band, because it's the difference between the pump and your carrier that actually defines the output. And so this was shown with Brion scattering, and we thought we can maybe also go in the chaotic regime and also use more than one pump to be able to do multi-frequency processing. And so these are still in the proof of principle stage, and so we are using two carriers where you can see in the time domain this quasi-periodic pattern, and in the frequency domains you see the primary optoelectronic oscillator signals, and you also see some signs of nonlinearity, which were promising for us. And what you then see on the oscilloscope is this nice bifurcation, which is indication we have this chaos in the system, and so that's what we are going to work on now with different tasks. And Diana has also some results to tell you about at her poster. Okay, now we have these things, and we were thinking, can we also use acoustic waves to optimize existing extreme learning machine? And in this case, we use a fiber-based extreme learning machine, and we use acoustic waves in the tuning of them to make it an evolutionary optical extreme learning machine. There's also a poster today by Oscar. So what is the system about? The physical system is first a highly nonlinear fiber where we do the mixing, and it also induces nonlinearity. Then we have the layer where we use acoustic waves to optimize the system. So we have basically handles to do something inside the extreme learning machine, which you usually don't touch. And then you have another highly nonlinear fiber, which you also use for mixing and for the nonlinearity. And then the training is done as usual at the end. So a usual workflow would be the following. You would have a classification task, you encode the data, and we use here 4-wave mixing. I know there are people from Mario Chemnitz in the crowd, so they use supercontinuum, which you could also use. And then usually you would go to the digital domain and do the training and have the prediction. And now we use this additional window here where we do optimization of the extreme learning machine and amplify several frequencies in this comp. And for this, we have basically more degrees of freedom, and then we feed it back into the digital domain. And as you can also see on these results, you are able to amplify the edges of the spectrum, which usually would go down and down with amplitude the further you go. So these are the spiral classification tasks if you don't use any Brion scattering. So it actually works already quite well, and a group of Mario Chemnitz has shown this. If you go to more complicated structures, the accuracy goes down. And so we had a look on both tasks. And if you use a genetic algorithm, you are able to find the right frequencies of your control pulses to be able to optimize the extreme learning machine. And so this would be the region where we want to work with. And here we could actually achieve to go from the 92% to almost 100%. And for the other tasks from 70 to 85%. And it's also work in progress, so we want to get better with this, because at the moment we are only using amplification of 2 frequencies. So one can also think about more of them and use also other knobs of improvement. Okay, Good. So some advantages of it could be we increase the performance of the extreme learning machine. It might be possible to go to a lower power consumption because we can use the frequency channels that are actually useful. And we're also able to maybe reduce the bandwidth that one needs for the detection. Okay, so I'm going to mention just a few topics on these other areas that we're working with, because I think they are relevant, and maybe this sparks also some nice conversation during the conference. Okay, so we also want to bring the optoacoustic interaction to the quantum domain, and if you have some background in optomechanics, that has already been done. But we are not in a resonator. We want to work with waveguides and fibers. So this is a continuum system which works quite differently. And we are working here on cavity-less strong coupling. We work on cooling of acoustic waves, entanglement, and also on a quantum memory where we have recent results, and it works very similar to classical memory, but for quantum states. I want to highlight this work because you have to imagine that usually if you have strong coupling in an optomechanical resonator, the light goes around the resonator 1 million times if you're lucky with your quality factor. But in a fiber and a waveguide, it only goes through once. So that's the only option where you get strong coupling, so to say. And we are very happy to be able to observe this. So what the theory predicted was a splitting in the anti-Stokes spectrum, which we very nicely see in the experiment. And we also see in a different experimental setup that there are these avoided crossings, which you can see basically in this picture. In terms of non-Hermitian physics, I wanted to mention also one work with a group leader here at the Institute. So they are working on theory of non-Hermitian physics, and we were interested in implementing such a structure in an optical fiber. So usually these exceptional points and other topological features are implemented in fabricated structures, so resonators that are the same size and so on. And we wanted to do this basically in the virtual domain, in the frequency domain. So we used, for instance, for an exceptional point of order 3, 3 frequency tones. And so Grigory was working on this experiment, so he's also here if you want to talk to him. And what is actually showed is quite interesting. So this is an experiment. So this is not some simulation of eigenvalue planes. This is really an experiment, every point, which you can measure in an optical fiber by using optoacoustic interaction. And it reveals, for instance, an exceptional point of order 3, lines of exceptional points of order 2, a Fermi arc, and so on. And so we have all these topological features, but in a, let's say, frequency domain in a simple fiber. And I mention this here because we see a lot of potential also towards computing in this case, because if we can link some of these structures, for instance, also if there is an enhanced nonlinearity, which is a big topic in the field, I'm not yet sure, but we could use this also for some calculations. We are also working towards having more energy efficient systems, and more energy efficient systems will always benefit from the fact if we have a better gain, a better coupling. And so we have, for instance, one platform which is a liquid core fiber, where we previously showed negative pressure in this liquid, but then we dipped it into liquid nitrogen and froze the fiber, and realized that there's actually a super high gain in this new structure, which is the same gain as, for instance, in soft glass fibers, which is super hard to fabricate, and that's actually much easier to work with. And here we also actually directly implemented a memory and saw that it's much easier. We have a better energy. We have a much lower energy consumption for this type of processes. Now, these were all on acoustic waves, but I also want to mention that we recently got into the field of spin waves, where instead of having Brion light scattering from acoustic phonons, we use spin waves, so magnons, that as a counterpart to optical photons. And one result that I wanted to highlight is that one can also have a look at the time dynamics in these spin waves. So we are mostly coming from this pulse regime, so that was something that interested us. And one can see that actually the lifetimes of these spin waves are much longer at room temperature as the acoustic waves. So we think that might be actually an interesting platform also to do computing in these kind of structures. And also spin waves can usually be tuned in frequency much wider than the acoustic waves can. Okay, so I will wrap up. I've talked a lot about our endeavors on optical computing with acoustic waves. I highlighted one topic on quantum information processing, on higher order exception points and optomagnonics. I did not talk about frequency conversion, so we are also working with orbital angular momentum modes in fibers, and I talked briefly about the liquid core fibers. I want to mention that there is a workshop in Erice again, for some of you have already been there last year. The deadline is still next Monday, so if you want to apply. I want to thank my group for the beautiful results and our collaborators. And with that, thank you for your attention.
Very much, Birgit. We have 5 minutes for questions, so plenty of time.
Thank you for the nice talk. So this is probably a pretty naive question, but if you observe these non-emission topological effects in the fiber, so how does this actually work? So you kind of you pump an acoustic wave and then you build some time crystal essentially that then has like a Bryan zone essentially?
So the Bryan resonance is basically has a gain and a loss spectrum in the Stokes and the anti-Stokes regime. And if you have this, if you go, let's say if you use multiple frequencies, you can actually leverage this combination of the different resonances and their combination to actually create a non-Hermitian system. So usually you would have this gain and losses that need to be balanced, and one can actually also do this with the effect of Bryan scattering. I'm not sure if this, maybe one can call this a time crystal or in the acoustic waves, but I think it's easier to understand from the perspective of the gain and the loss in the Bryan spectrum.
Thank you.
Normally the Brillouin interaction is very narrow band, and early on you mentioned that you could even have, you could isolate different frequency bands. Mm-hmm. But with optical computing, one of the promising features is that it's very broadband. Mm-hmm. So my question is, does having optoacoustic computing, does that limit the bandwidth that you can use to like this Brillouin interaction, or am I getting it wrong and actually you can harness the full bandwidth of optics?
So I think it depends, because you are then referring to how short these pulses can be that you can use, right? So if we could show that we can do this with 100 picoseconds pulses. So if you want to go to femtoseconds, that's probably not possible. Maybe actually also because there are some optoacoustic interaction with femtoseconds. But if you stay within the telecom regime of picosecond pulses, then it should still be possible. And also, I have the impression we shine light on different sides of the problem now with Bryan scattering, and so it depends on how you want to use it. So, for instance, for the weighting of an extreme learning machine, you would actually use this narrow linewidth to put weights on different frequency channels. But for the memory, if you are longer than 100 picosecond, it's fine. Yeah.
What sense the 100 picosecond?
So, okay, this is the experimental result that we proved. It can probably also go shorter, and it depends on the gain of your medium and the line width of your Bryan frequency. So if you get into a gain, like I said, this high gain fibers, where you have super high Bryan gain, you are able to go to shorter pulses. And you can imagine this like the acoustic wave needs time to build up. It's slow. But if you have high gain, then this little bit in the beginning is already sufficient to do some processing for you.
That's very clear. Thank you.
Any more questions? Clara?
Thank you very much for the very interesting talk. You mentioned in situ training, I think, in the context of the recurrent neural networks. What did you use specifically in this case?
So there's the experimental setup where you have the data coming in and the control pulses, and you change the frequency of the control pulses and feed it back via via the computer, and do at the same time while you are running the experiment, you optimize the separation of the overlap of these states that you want to observe. So what you will have is, let's say you have like maybe 3 pulses on which you encode 3 amplitudes. And what you want to do is to distinguish AAA, AAB, and so on. And so what you want to have is that there is as little overlap as possible. So as you use this overlap as a loss function. And while doing the in situ training, this overlap gets smaller and smaller.
A digital model of a digital twin, basically, of your.
Should we call it a digital twin? No. So I think I know it's a feedback, so it's not a complete system, but it's a feedback loop. Yeah.
To hear more about it.
Any more questions?
Maybe a very big one. Yeah. So, can you, very nice talk. Can you comment a bit on the strength of the interaction? Because people like resonators, because if you collocate something for a million periods, then you get a strong interaction. But how do you do it here? It's a material.
So it's the material that is, for instance, it works very well with soft glasses because it's squishy. So you need to, basically what would be a good thing to have is like a material that acts nicely for acoustic waves and has low optical losses. And that's hard. So to have both of them is not so easy. But for instance, tricotinide chips work very nicely because the material is soft, but the losses are not as good as in optical fiber. So you need to place yourself into a position where you have the best gain out of it. And that's why we are actually working also with all sorts of different platforms, because sometimes it makes sense to have much lower optical losses. Sometimes it makes sense to have much higher interaction of optoacoustics.
Very cool that you have this design freedom.
Yeah, thanks.
Okay, thank you. I think with that we close this session and thank Birgit and all the speakers of the session.